Good morning, everybody. Or for you, it's good afternoon. For us, it's good morning.
Good afternoon.
Before we start introductions, I would say we give around 3, 4, 5 minutes for everybody to be able to join. And after that, we're going to start with the webinar. Kaushik, if you have an overview of how many of the attendees have joined, you can just throw in when you think that most or all of them are here, and then we can start.
Yeah, absolutely. I think we'll wait for a couple more minutes.
Okay, yeah, that's perfect. A very warm welcome from my side. My name is Christian Deidelmeier. I'm a scientist here at V&F Analyse und Messtechnik in Austria. We are a provider of online mass spectrometry, and today's topic of this webinar will be a short presentation on hydrogen purity analysis and the device that we have developed in order to do that, which is called the HydrogenSense. I would like to thank very much Kaushik Shah from our partner in India, which is Matashit Industries, for organizing this meeting and for sending the invites out to all the attendees. Kaushik, I don't know, do you want to say some words before we start off?
Yes, I just basically want to thank all the attendees for taking the time to attend this event. Hydrogen purity is a very tricky business, and hopefully at the end of this session, they'll see the advantages of having a V&F HydrogenSense, the technology involved, and really all the hurdles that we have overcome already, and make it an easier experience for our customers to be able to test their hydrogen purity.
I would like for everyone to keep their mics muted throughout the presentation, and then the short demonstration of the device afterwards. And we will go into a Q&A at the end. And if you have pressing questions or open questions, we have some time allocated for that in the end. As you've seen, this material here will be recorded. So we're going to make a polished video out of that, which will then also be shared with Matashit. And if you want it, you can get that after the post-production is finished. So in the beginning, we're going to start with a short presentation, which will give you an overview of the measurement task. Okay, today we're going to talk a little bit about hydrogen purity analysis, and especially with compliance to 2 regulations, which is the SAE J2719 and the ISO 14687. Both of them regulate different types of hydrogen quality, but currently the most pressing one and the most interesting one is the quality for hydrogen fueled vehicles. So typically right now it's PM, so proton exchange membrane driven vehicles, where the regulation is very strict. So the contamination in the hydrogen may only be very low. Regarding the content, we're going to go a little bit over the background, present the solution that has been developed here at V&F, some advantages, some possible setups. Then we're going to have a look on slides on how this measurement is realized with our online mass spectrometers, and also the auxiliary devices that we use in order to do that. And afterwards, we're going to stop the presentation and we are going to have a look on the hardware itself. And then we're going to operate the instrument. I have set up a few calibration gases so you can get an impression of what's going on when the instrument is faced with certain concentrations and how the signals are depicted there. Right, regarding background, hydrogen purity, regarding with those 2 regulations, has now been around for quite some time, since we have had this surge in alternative energy and also getting away from fossil fuels in the mobility sector. And right now, the proton exchange membrane driven cars are still like the technology to go if you want to have like a technology which can deliver power when you need it, for example, during acceleration, but also have almost zero emission. It's pretty much just water which comes out of these devices. But the issue with these fuel cells is that they, at the current point, cannot tolerate, I'm sorry, I just have to admit a few more people. Sorry for that. They cannot tolerate certain impurities which can be in their fuel, which is 100% hydrogen. And depending on the technology on which these fuels are produced, so like the most pure way would be electrolysis, but there are also other ways to do it with steam reforming through pressure swing absorption, generating again CO2 in the production, but still hydrogen is the final product. And the impurities that can cause damage are rather vast, and especially the concentration ranges where these impurities may cause damage to a PM fuel cells are very low. This is especially true for sulfur components, but the regulations, of course, cover a wide variety of chemical compounds which need to be monitored and need to be proven to be under a certain threshold in order for the PM fuel cells not to take damage. Our solution for that is called HydrogenSense. It's a double mass spectrometer, which on the one hand uses our patented in-house technology, which is ion molecule reaction mass spectrometry. And as well, we have a secondary spectrometer, which is a conventional electron ionization mass spectrometer for some of the compounds which we cannot cover with our proprietary ionization method. Maybe a little bit of history to our company. The company is now a little bit over 30 years old and started out in the, I'm sorry, there's still people pouring in. I have to break again. The company started out in automotive industry. So at the time when the first exhaust gas treatment catalysts were implemented, the people in the automotive industry needed a fast solution to monitor certain compounds. This is how the device that we are now using as well for the hydrogen purity analysis came into life. And over these 30 years, loads of things were improved, of course, but the general principle has still remained the same. So it is an online technology which does not use any pre-concentration or other sample preparation. It's just the gas comes from the point where you want to measure it. You have to transfer it to the instrument, and there it will be analyzed in real time. The very beneficial thing of this technology is that it has a really vast amount of compounds that you can cover within one instrument. So loads of mass spectrometers can do that, but with our patented ionization method, there are a few key benefits and which allows us to do things that other mass spectrometers can't do. So here is a short overview of which kind of sampling points we might be faced with and what can be done with our instrument. So we're looking at the complete life cycle of the hydrogen until it is then reacted in the PM fuel cell. So we're talking production sites, we have storage sites, we have transport, then fueling station, and the car itself. So right now, a major league installation, we haven't done it yet. So the instruments that are already in the field are usually used in a stationary environment where gas from these sites is then transported in a suitable gas cylinder to the instrument, which is then attached there, and the analysis then proceeds in a closed location, like a lab or a room or a container. But in principle, with the right gas treatment and the installation of piping and all of that. In principle, once these things are established, you can also provide the gas to the instrument from any of these sites. So we see here it's quite a massive machine. So we're going to have a look at it then later on the camera. It's roughly 2.2 meters high. It is all housed in a climatic cabinet. And all of the insides we're going to have a look at just later on during the live demonstration. In principle, inside we will find a IMRMS and EIMS mass spectrometer, auxiliary devices for compounds that we cannot cover with our own technology. And also there is space for industrial PCs, UPSs and things like that, should it be necessary to be present on site. So this is a very, very short introduction of what are we doing actually in order to measure all these compounds. So in principle, mass spectrometry is something where you will introduce a gas into a evacuated vessel. And what you will then do is you will have to use some form of ionization to get the impurities in the gas into a charged state. So what we use is we're using positive ions in order to do the analysis. There are two ways to do that. We have here the conventional electron ionization source, which will just bombard the gas with electrons. And we will have a quadrupole mass filter in order to separate out the mass of the compound that we are interested in. And for our IMRMS, which is a soft ionization principle, we are using primary ions at 10, 12, and 15 electron volts of energy, which will then collide with the gas that we want to analyze. Then the filtering, so the mass filtering in the end is a quadrupole system. And the detection system here is a single ion counter. So what we use this part of the spectrometer for is the very low concentrations. And the IMS is mainly used for the stagnant components. So it's used for argon, for helium, and for nitrogen, which also in the regulations are allowed at a much higher level of a 500 ppm or 300. I'm not sure about the latest release that they brought out. So these ones will be used only for 3 components, and the IMRMS spectrometer will be used for all the rest that we need that in order to produce the signals that are regulated in these 2 documents. So this is a brief overview. I think that all of these data we can share later on. So this pretty much just gives the specs of the 2 instruments that we are using. In order to keep time a little bit short, I would leave that for you to read by yourself, and also maybe get into contact with Kojik so he can give you some closer insights on the performance that you can expect from these instruments. All right, so now we're going to the compounds. So we're going to see that in these regulations, loads of compounds are regulated, and we're going to go over a few of them. Especially one thing that is important to understand is how we use these spectrometers, the mass spectrometers, in order to cover total X compounds. So like total hydrocarbons, or their total sulfurs and total halogenated. All of those are regulated in a way that, since mass spectrometer is not a device that can really do a total analysis, it's a targeted single compound type of analysis device, meaning that I can analyze methane and I can analyze ethane and so on and so on. So there's loads of things that you can analyze with it, but I don't have a single signal in order to produce a total signal of something. So what we're doing is we are using the asterisks in the regulation, which specify a certain amount and a certain type of compound, which is like the things you can use in order to produce a total signal. So for example, for total sulfur, you should use at least H2S, CS2, COS, SO2, things like that. And these are all compounds that we can implement in the spectrometer. Later on, we will get for each of these compounds an analysis result, and the total value will be produced by simple summation of all of the individual signals that we have acquired. So here again, these are the kinds of the regions which you can reach for the LOD. So this is the limit of detection for the compounds which are specified in the regulations. There are two exceptions here. So carbon monoxide and water is something where our technology struggles a bit. So in the last year, we have switched to auxiliary devices in order to quantify these two compounds. And we see here, for example, total sulfur on our device is produced as a summation of hydrogen sulfide, carbonyl sulfide, and carbon disulfide, and different malcaptans. So this is just the carbon sulfur components. Formaldehyde and formic acid can also be easily quantified on this device, as well as ammonia. And again, for the halogenated compounds, we are sticking with the regulation. So we have organic halides, chlorides, and hydrogen chloride, which will then be summated to produce the total halogenated compounds analysis result. Now, what is special about this device? So if you look into these regulations, there are standard methods available for most of the compounds that are stated, but typically this would cause to have a rack of about 5 to 6 analyzers in order to be able to do that quantification. So what we wanted to provide here is we wanted to use our technology in order to provide a singular housing for instruments which can do the analysis all at once and in real time if necessary. So you, with the HydrogenSense, we have managed to do that. And the thing is also that real time, like the analyzer is a real time concept, but since we are looking at very low detection levels necessary, we're talking about an analysis time of roughly 15 minutes in order to quantify everything that is required within the ISO regulation. I've already mentioned, so we are not using pre-concentration or sample preparation. It's pretty much sample gas goes from point A to B, then comes into our sample switching module, and will then be introduced into the mass spectrometer. Something that we offer, but which will not be covered in this webinar here, is a fully automated solution, which is pretty much a piece of software that we currently call Premier Guard. It is it's a device which has an auto scheduler, which has all kinds of certificates, printing, calibration, gas supervision, and things like that. For example, for a site, when you're on the production site and you want to schedule analyses within certain time frames, then this can all be done in a fully automated way. Here, during this webinar, I would rather go into the basics and show you how signals are produced, how the instrument responds, and how an analysis can be done. All right, if we go to an installation of a device like this, there are always prerequisites. So what we are going to do is we're going to, of course, deliver you the device. We also have a smaller sample switching unit, which I will show you later on. But the prerequisites that we need, which we do not provide with the instrument, are zero and spun calibration gas cylinders. So this is a type of instrument that needs calibration gases in order to establish all the correct factors to do the measurement properly. Then piping and tubing from sample points, especially if they are further away. So let's say you have an industrial plant where you have to go a few hundred meters from sample point to analysis room. This is not something that is within our expertise, so this is not something that we can provide. And also pressure reducers for sample points and gas cylinders. And external control PC we can provide, but typically it makes more sense to buy it through the company and through a local supplier. And here is this small auxiliary device, which is called Valvebox, is something that is also essential for the analysis because this provides an easy way to connect sample points and calibration gases to the mass spectrometer. It is in principle a 16-port multiplexer, which is controlled by RS-232 from the spectrometer itself. This is something that we are going to see in, let's say, when the presentation is over. All of the interior is heated and filled with coated materials so that we don't have any surface loss of contaminants while we are introducing the hydrogen gas into the mass spectrometer. Inside, there is also a mass flow controller. This is mainly for an application when you have gas cylinders which don't have a lot of volume or a lot of pressure. Then we can regulate the amount of gas that is used by the instrument in order to be able to have sufficient gas to do a complete analysis. And here on the next slide, we see a potential measurement setup. So we see here, since there is a lot of compounds required to be quantified just from the regulation, we have quite a few calibration gas cylinders. So in this case, these are 12. We have a zero gas and 11 spun gas cylinders, which are all connected to an individual port on this multiplexing valve. We then have open points for hydrogen sampling or from a connector when you want to connect a bottle which you have on site. All of these positions are automatically controlled by our software. So it's pretty much just a click of a mouse in order to select one of the positions. Then once the valve has switched, the gas will be provided to the mass flow controller, where we have a heated line which goes towards the mass spectrometers, and an overflow line which will bypass all the gas which is not used by the spectrometers. This one I will just show you briefly. This is like the our main piece of software which can control an instrument, but we are going to see that live in just a few minutes. And here, this is something which we will also see live in just a few minutes. Sorry for repeating myself, but this is a demonstration of how fast the system will respond to a change of signal. So here what we have done is we have applied a calibration gas containing BTX, methyl mercaptan, and hydrogen sulfide. So we see here, before we were applying pure hydrogen, then switching to the calibration gas. So you see within one cycle of all the compounds, there is pretty much, depending on the stickiness of the compound, we are immediately at the expected level, which comes from this cylinder. There are some compounds which take a little bit more flush time, like this one here. This is hydrogen sulfide. But we will go into flush times and this a little bit more in detail when we do the live demonstration. And here is another graph, which is a repeatability study, where we have done, we've used the same gas in order to demonstrate the stability of the instrument. So once it's calibrated, and this one here is an application of the gas every 2 hours, you see that the concentrations are very reproducible throughout the day, as long as you do analyses. And yeah, calibration intervals, we're also going to have a talk about it a little bit later. Okay, so here is a few reference that we already have with this type of instrument, which I will also keep for you if you want to have this presentation. Kaushik Shah from Mattershitz Industries will gladly be able to share it with you. And so for now, I'd like to thank you for your attention, and we're going to go into the next phase, which is looking at the instruments. We see here, black is sample transfer line. The triple connector in the bottom is exhaust. The two data cables are used to control the valve box. Then we have main power is the glowing switch. Then once we follow this one here, we see here front view of the valve box. You see I have connected 6 gases right now, which are placed behind here. So we have 2 types of pure hydrogen, a 6.0 and a 5.0. And so here we see the valve box is pre-configured to supply on the one hand our instrument. This is the black line, but also auxiliary devices. So here we have a sample 3 and a sample 2. These are usually Siemens and Ametex devices that we use for CO analysis and water analysis. So we can have a look inside. On the inside is, we're going here into this heated container. This is where all the lines will go to to the multiplexing valve. Afterwards, we are going through the mass flow controller, then provide the gas to the mass spectrometer and to the auxiliary devices. And then we have some power supplies, heating regulators and things inside in order to keep everything warm and to avoid any of the potential contaminants to get stuck in the multiplexing unit. Go to the big device. So you see here, it's a usual cabinet. You can open it on this side. So here on the inside, we will find in the bottom is the mass spectrometer. So it's a little bit hard to see because it's all integrated. So we have on the top edge, we have vacuum chamber for electron ionization mass spectrometer. Bottom chamber is for IMR mass spectrometer. All of these devices are electronics, generators, and things like that. We have here a UPS, the Siemens CO analyzer, and here in this case we have an industrial PC which can run the full automation software, but this is not something of today's scope. So if I may, I'll give you a short overview of the software that we are using to control this instrument. So now you should see the main interface of our mass spectrometers. On the surface, it looks quite simple, but loads of things can be set up here. So basically, we have different modes of operation for these devices. So we have a measure mode, a standby mode, then a calibration mode. This will trigger an automatic calibration. And here on the most basic level, we have the possibility to just save data that we want to acquire. I will start this save right now because we are going to have a look at the data file in just a few minutes. So on the top center, you will see here is the definition of the measurement method. And you see, of course, you can have an indefinite amount of measurement methods. This one is called hydrogen purity, and it consists of all of these compounds that we see here in this list. So you will find pretty much a little bit of everything. So we have here, for example, a halogenated compound, which is tribromomethane. We have hydrocarbons, we have sulfurs, we have nitrous compounds like ammonia, formaldehyde, and so on and so on. And on the very bottom, this is what I've mentioned before. This is where we produce the signals that are actually regulated on the ISO regulation. So we have total volatile hydrocarbons with methane and without. Then we have a total sulfur, total halogenated, and then we have the individual compounds like helium, nitrogen, argon, which are there as individual signals, as they are also regulated as individual signals. Up here we see these are the sample inlet definitions and the sample inlet pressure. The sample inlet pressure is a rather key device which affects the performance of the instrument. So this is something that I will not be able to change because this is not something that you should be able to change. And here we have all the different positions of the multiplexing valve. So meaning that once I change an inlet here, the multiplexer will go to its correspondent position. And each of these inlets is also connected to a certain flow rate setting of the mass flow controller. So for example, if I'm switching here to position 03, this is a calibration gas bottle which contains helium, nitrogen, and argon. And in order for you to get an impression of how these measurements work, so you can imagine it like this. So each one of these molecules is pretty much a set of parameters for the instrument. So the measurement will proceed on one molecule, and then it will go to the next. Once this is finished, then it will go to the next, and to the next, and to the next. This is why we call that the measurement cycle. So the instrument will go indefinitely from top to bottom and acquire the corresponding signals for the gas which it is currently analyzing. And we see here, right now, we have a single cycle time for the IMRMS spectrometer, which is 37 seconds or 37.5. And we have about 3 seconds for the EIMS molecules. So on top, also on the surface here, it looks like everything is one cycle, but actually these compounds here, these are all measured with the ion molecule reaction mass spectrometer, and the bottom 3 here are measured with the EIMS mass spectrometer. So this means that you actually have 2 cycles, and they are then integrated, and the data is collected into the surface that we see here now. And for example, here on this gas, we will see we have 1,000 ppm of helium, 2,000 of nitrogen, and 1,000 of argon. And we have roughly 50,000 ppb of oxygen in this bottle. And you see here the change in signal, so the response time is pretty fast. So you pretty much switch over the position, you apply the new gas to the spectrometer, and then the instrument will show the values in this gas. We can maybe try and switch to another bottle, which is connected to position 4. And this is a bottle which contains, it's a multi-calibration gas bottle which contains the halogenated compounds that we are using to produce the total halogenated signal. So here, for example, we have tribromomethane, tetrachloroethylene, dichloroethane, trichloroethylene, and dichloromethane. All of these which are in this calibration gas bottle. And once we give it a few cycles, we will see that here upon switching the gas, we are pretty much already getting very close to the nominal concentration in this bottle, which is either a 3,000 ppb or 5,000 ppb. And so you see here that the distance for each of these data points will always be the cycle time. So here, a new line of points will be produced within 37.5 seconds. And what we usually advise people to do is, in order to do proper analysis with good statistics, I mean, you can only use one measurement point, but typically it makes sense to have a certain amount of flush time and to have a certain amount of measurement points where you can build a average value and a standard deviation in order to get a good impression of the quality of the measurement that you have just done. So maybe we're gonna have a look at another bottle. This is the bottle that we actually just have seen in the presentation. So this is the one where we have a BTX, so xylene toluene benzene, hydrogen sulfide, methyl mercaptan. And I need to wait, but probably there's something else in there. So here right now, these are the signals that will be the relevant ones. And what we see here as well is like the specificity of the spectrometer shows you that once you change the gas, so here we had all of our halogenated, so brominated, chlorinated compounds. And once we switch over to now a bottle with sulfur components and hydrocarbons, it is pretty much an instant change. So you will get very quick response from this type of device. The thing is usually once new sample lines are attached, so like the initial flush time is one of the most crucial thing which might cause you issues in response time, or also really in final saturation. From our experience, the most problematic compound is oxygen here, because usually when you attach a new gas or you have an improperly flushed line, you will have ambient air in that line, meaning that ambient air contains around 20.8% oxygen. So in order to flush all of that out, that is something that needs to be done very diligently in order to get a proper reading for the oxygen content in the gas that you want to analyze. So usually what we recommend is, right now here we are pretty much only looking for a few minutes, but we typically recommend to have a flush time of at least 5 minutes. So in order to get really the essence of the gas that you want to analyze into the spectrometer, then we run like 5 or 10 measurement cycles in order to produce the final value of the analysis. So I'm going to switch over now to position 1, which is a 6.0 hydrogen calibration gas bottle. So this is our zero reference, you could say. So this is also the gas that we would use in order to perform the zero calibration. So pretty much going to give it just a few cycles for all the signals to go down. And so you will see here, like we still have a large number on that summation, because this is why this is because the summated values are only calculated once the measurement cycle is done. So once all the signals have been acquired, then the signal will go down. In principle, so right now the instrument will always give you data, and it's pretty much just a matter of evaluating that data. So for example, if I'm going here, so on position 2, I have a 5.0 standard hydrogen. So in principle, what we are doing now is we are acquiring signal on the 6.0 standard. And once we switch, I just need to put that down. You can make notes in the software so that later on, once you look at the file, you know what you have done. All that up. Pretty much once we switch here, now the gas from the hydrogen 5.0 bottle will be supplied to the instrument. And what we would do is we would just let the analysis run for, let's see, we have around 40 seconds. So for around 5 minutes, this should give us enough data points to do the evaluation later on. And so we see here, I chose this gas in specifically because I know that this hydrogen 5.0 has a little bit of excess helium inside. This pretty much comes from the way it has been produced. So it's probably a steam reformed type of hydrogen, which tend to contain a little bit more helium. And we can then have a look at the acquired data. and do a brief evaluation in order to see how the final measurement results will be or can be computed. So this is like the really basic manual way in order to do that. But of course, with the fully automated solution, this is something that can be easily done in a fully automated way. So for now, I think we have roughly 5 minutes of data acquisition. So if there are already some questions, we can use a short amount of time to answer them. And then we're going to continue on with the evaluation, and then we're going into the Q&A properly.
So we encourage participants to ask any questions so far that you might have while we wait for more data to get gathered.
So you mentioned about CO, carbon monoxide. So you cannot meet the carbon monoxide limit as per ISO standards?
I'm sorry, I've lost my headset again. I didn't understand the question.
Christian, can you reconnect your headset? Because we can also not hear you very clearly.
Hello, can you understand me?
Yes, we can hear you.
Perfect. I hear again. Could you please repeat the question? I'm sorry, I seem to lose connection on my Bluetooth device.
Yeah, can you repeat on carbon monoxide, like what is the, the least detection limit for carbon monoxide?
For carbon monoxide on this Siemens analyzer that we are using for it, it's 100 ppb. So it's pretty much at this stage, like the limit in the regulation is 200 ppb. So it pretty much gives you a good or a bad criteria. So that the quantification will not be as precise as like you can say it is a 15 or 20 ppb. You can pretty much say, all right, it's below 200 or it's above 200. Okay, I think we have enough data to have a look on how we would analyze what we have now acquired on the 5.0 hydrogen standard. So what I'm going to do is I'm going to click here on stop in order to finish the file that has been saved. I'm sharing right now the view of something that is called V&F history. It's a very simple program to do evaluations. So like it's very basic mathematics, which can be used to produce the analysis result rather quickly. Just gonna put some points here. So here we still see these were all the signals that we have acquired. So our 3 calibration gases, and you will see once I zoom into certain data range, then I can see the results for that data range. So for example, here I have 997 and 1995 for the calibration gas bottle, which contains all of these compounds. So what we want to do now is we want to go back out. And here, this is where we have put this notification. So this was the point where we switched onto the hydrogen 5.0. So I'm going to use like these 5 points here in the end. This gives me mean values and standard deviations directly from the data. So it's nothing calculated. It's really from the data that has been acquired. So which should show us that here in this 5.0 gas, we have 32 ppm of helium. Then we have 5.6 ppb hydrocarbons with methane, 5.8 without methane. We have total sulfur of 1.4 and total halogenated of 1.6. So these would be the results for the summated compounds, and all the other compounds which are singularly to be quantified, for example, like formic acid was not detected. Formaldehyde was just as well, was not detected. I'm just having a look. Carbon dioxide was not detected. And yeah, apart from that, ammonia as well was not detected. So this is mainly to give you an overview of how the analysis proceeds and how the values are produced. All of this, like what the values are, what the standard deviations of the measurement are, this is all something that can be automated if necessary. All right, so that was pretty much it from my side to give you a brief overview of the HydrogenSense and its measurement capabilities. So I thank you all for attending and for your time. And so we can now probably go into a Q&A session for everyone or for anyone who has further questions. Thank you very much.
Yeah, I have a question like, have you got inquiry about measuring KOH because hydrogen coming from electrolyzers can have KOH if the purification system is not working properly?
Yeah,
So have you got?
I've had that inquiry, but the problem is that the device that we are using is a purely gas analyzer, and I'm not sure if KOH, what's its if it's then gaseously solvated, because like these types of compounds are hard to connect or hard to detect, like without using wet chemistry, for example, like pH analyses and things like that. So we've had the inquiry, but it's not been further studied on our instrument. So I can't really tell you if it's possible or not.
Okay. And also like why in ISO standard in this KOH?
Why it is in there, you mean?
Yeah, I mean, have you heard that in ISO standard KOH component is not listed? So have you came across instance where again the ISO standard will be updated or there is a request to update what should be the limit of KOH when the
Yeah,
hydrogen is going to fuel cell vehicle? Are you aware of it?
I think it was the other way around, but I can't really say that I know that for certain. I think that in an older regulation of ISO, there were like these ions, like sodium, potassium ions, they needed to be quantified. But I think that in the latest one, they have removed that. I'm not quite sure though. So for us, like we can handle pretty much all of the gas components, but there is still in the ISO you have necessity to also analyze particulates, so like dust particles, which is something that our devices cannot do. So this is something that needs to be acquired separately from our device.
Okay, thank you. And just one last question. If this analyzer have to be used in an offline condition, as I understand, this is this device needs a continuous flow. But if
Yes,
I
exactly.
use it, but if I use for offline, like in laboratory, how much volume of gas would be required and at what pressure typically?
Wait, I can show you that really quickly. I need to restart the screen share. I'm sorry. So my screen is visible again.
Yeah.
So you see here, these are service panels. These are pretty much just the windows where you can check on the actual values of the devices used. So right now, here during operation, I would have set a mass flow rate of 500 milliliters per minute. This is something where I know that like it's enough gas to have proper flush time, and you don't need to wait a long time for everything to saturate. But during a standby mode, you can also reduce that. So there are multiple settings for that. So the lowest that I would recommend during like the instrument is due to its vacuum vessels, which always need to be pumped, the instrument is always running, even if you don't do analysis with it. And during that time, I would flush it with a hydrogen 5.0 standard at roughly 150 milliliters. This should be enough for the downtime when you don't use it. And once you switch back into operation and you want to do analysis, I would recommend to go back to 500 milliliters per minute.
And one cycle takes, as you mentioned, I think what 30 minutes, I guess you mentioned, right?
One cycle is 37 seconds. This is displayed down
37
here.
seconds. Okay,
Yeah.
okay, seconds.
So you would run like if you run 10 points after the flush time, that would take you 40 seconds times 10 is roughly 5-7 minutes or something. Like to do it very diligently, we usually say roughly 15 minutes, including the flush time, is the time it will take to get a proper measurement result.
Okay. And you mentioned that even if we are not analyzing it, it would still need some hydrogen running through the system. So basically, there will be a hydrogen cylinder required, which would be always giving some hydrogen in case the plant hydrogen is not available.
Exactly. That what is the way. If you do it like this is the most stable way to operate the instrument. I mean, this is going rather deep into the technicals why this is necessary, because you can run the instrument on pretty much any gas, but there is a certain chemistry on the ion source parts of these devices once you apply hydrogen. So there is hydrogen has very high reductive properties, and ambient air has oxidative properties on the filament material, meaning that when you switch between the two, there is a certain stabilization time until the instrument is completely saturated in the new gas. And that is why we typically recommend to have the hydrogen running. If you know, all right, I don't use the instrument now for 3 or 4 days, then you can stop the supply, put it into standby. The only thing you need to remember is that before you want to do the analysis, you should give the instrument about 24 hours on the hydrogen gas in order for everything to be saturated out.
Okay, thank you.
Means how much minimum pressure is required for this sampling?
Minimum pressure on the Valvebox inlet is slight overpressure. I think it's half a bar. So it's 1.5 bar absolute or 0.5 bar gauge in order to operate the mass flow controller.
And
also,
maximum is,
the maximum is the bigger problem, because this multiplexer is only certified up to 5 bar gauge for hydrogen gas in order to be tight. So we usually recommend to have pressure reduction beforehand and set the pressure into the safe region of the multiplexer.
So instead of this hydrogen saturation, can we do the nitrogen purging also? That is also possible or not?
You can do it, but my experience is that switching into hydrogen is something that will give you I mean, it's not much, but it is noticeable on some compounds that you will get excess signal on a few of these compounds measured, because you will solvate them out of the hot filament material. I mean, these electron sources burn very hot, so they are around 1500 degrees. And when they come into contact with hydrogen, then some chemistry happens at the surface. So even if you flush it with nitrogen, a change from nitrogen to hydrogen is faster, but it is still something that needs to be saturated out. So because, like, especially for the sulfur compounds, where you really need to have like sub ppb detection levels for the individual compound, I mean, this is something where we really recommend to have the hydrogen running for at least a day in order to get those backgrounds in the hydrogen to the correct level, and then be able to perform the analysis in the right way.
Okay. Because my question is, because if I want to keep it for maybe for one week, maybe for 1 month in idle condition, so you mean to say I have to put some nitrogen, then when we'll again we'll take it in line, So we'll run the hydrogen 24 hours. Then it is, I think there is
Exactly,
also.
exactly. Yeah,
Mm,
that's perfect.
mm.
That's perfect.
Okay, okay. Okay, is there any temperature limitation?
A temperature.
Mm-hmm.
So this type of climate control unit, I think it can operate up to 35 degrees ambient temperature.
Mm-hmm.
But I'd have to recheck that properly. This is something that we have in our brochures, so that we guarantee that it works up to 35. Probably there is
Mm-hmm.
some window in there, but it's like putting it somewhere where it's 50, 60 degrees. This is not going to work.
Okay, up to 80 also, because normally it comes out from the electrolyzer part from the 80 degrees centigrade like this only. So that is also okay for you. No, it is not a problem. You meant to say?
I'm sorry, the last
No,
sentence I
no,
didn't
no,
understand.
no. Normally, from the electrolyzer, the hydrogen is coming out at the temperature of 80 degrees centigrade.
Ah,
80
yeah,
to
okay.
90
Now
degrees
that's not
centigrade.
an issue. We are
That's not an
post
issue.
heating
Mhm.
everything inside, so the gas will have a temperature of 100 degrees coming from the valve box and then going up to 110 degrees in
Okay.
the instrument.
Okay, okay, fine. Okay. Thank you. Thank you.
I have a doubt. Can we measure the moisture content in the hydrogen?
Not on the spectrometers, but we use an auxiliary device for that. It's called MA-Tech. It's an American company. They build very highly sophisticated water analyzers.
Okay, so using the hydrogen sense, if there is some percentage of moisture in the hydrogen, your system will not be able to detect it.
There will be an auxiliary instrument in the climate cabinet which does the water analysis.
Okay, and your system is safe from any such contaminant?
I'm sorry, I didn't understand the last thing.
The hydrogen sense, it is safe from any such presence of moisture in the hydrogen.
Yeah, the moisture is not an issue. The instrument, you can pretty much run multiple volume % of moisture into that instrument. The thing is, for our technology, the very low levels required, which are currently 5 ppm, this is not something that we can reliably quantify using the IMRMS principle. That is why we're using an auxiliary device. But in principle, the instrument can detect moisture, and it's also possible to have loads of moisture in the instrument. It's just the thing is what we always need to take care of is that it is non-condensing moisture. So it needs to be gas phase moisture in order to be able to be analyzed.
Okay.
Yeah, my one question related to the previous questions. The simple quantity, in case if you are using offline as offline, in the case keeping your instrument in the laboratory area.
Mhm.
So typically, if I am collecting sample in the 500 ml sample cylinder, and let's say about the 5 kg pressure, will it be able to, I mean, give the right result? I mean, precise and trusted result?
That's something that needs to be calculated. So for analysis, I think we've seen it before. So right now I'm running 500 milliliters per minute. Let's say I need 15 minutes of analysis time, including flushing and then doing the measurement analysis. That would mean I need at least 7.5 liters of gas. At a 500 ml container, that should be roughly, what is that? 15 bars of pressure. So I would rather go to 20 bars of pressure in order to be able to have enough gas to do the analysis.
Okay, okay.
Or another way to go would be to have a bigger container using a 1 liter or a 2 liter container at a lower pressure. But that is always something, it's a good question, because that is something that you need to have in mind, especially when you're transporting samples from point A to point B in a closed vessel. So like gas cylinder or a gas bomb, we call it, these round devices. You need to have enough gas in there in order to do the analysis then on the device, because it will consume a certain amount of that gas.
Okay, good. My second question is, you said about the moisture you are providing, some different analyzer. So on what technique it will work?
This I think now you've caught me off guard. I actually do not know.
Yeah.
I don't know
No,
if
sir.
it's a microgravimetric scale, I think, something like that. But I can provide that to you. I have to look it up. I'm very sorry.
No, so coming back to compliance of these techniques, what you have presented. So the moment we are looking at the different ISO methods, standards like 14687 is a standard for hydrogen specifications.
Mhm,
Then further, ISO 21087 is talking about the what technique should be used to measure the particular contaminants in the hydrogen and how to
mhm,
measure the purity or what it may be. Uh, Further, it is 19880 is also talking about the fuel station hydrogen quality. So all these three standards is talking back to the 21087 about the analytical techniques, test methods. So does your V&F techniques comply to 21087?
So right now we don't have like any official mention in these types of regulation. This is something which is still an ongoing endeavor, and it is unfortunately very time consuming. So we are trying to get listed as an official device which can be used for that. But at this point in time, we do not have this status yet.
Okay. My next question is, what will be, what is your recommendation about the frequency of calibrations?
Yeah, this is a very good point. So what my experience is that it makes sense to have a background calibration before each analysis. It's just especially for the sulfur compounds. I mean, like 1 ppb of background offset is something that can easily occur. So what we usually recommend is to have background calibration before you switch to the gas that you actually want to analyze. And for the sensitivity calibration, this is something that I would recommend to do twice a week.
Twice a week. Okay. Coming back to the core question about the calibration standards, you said it is not in your scope of supply. It will not be
No.
in your scope of supply. So my next question is, there is a lot many ambiguity. There will be ambiguity in the standard quality. Like typically, ammonia, formaldehyde, acetaldehyde, even sulfur species or halogens. Different halogens have different boiling points. How to make sure that it is in the same phase or something. So in this situation, how you are ensuring that the users are able to calibrate your instrument appropriately and getting the right result, because getting right standard itself is a challenge.
Mhm.
uh, so would like to know from you your
Yeah.
input from
Yeah,
you. Yeah.
we've had issues with that in the past for a long time, but fortunately the we have a supplier now, which is an Italian supplier. They have an excellent lab, and uh, to our experience, they also know very well what they are doing while making calibration gas standards. So what we have done is we had like a half a year trial with their calibration gases. So what we did is we tried to match the concentration in the bottle and monitor them over time. So we had like a standard bottle that we've been using for a long time. It's from a different supplier, and we wanted to see if the compounds that they mix into the hydrogen gas, if they stabilize well over time. And that was something that we were very surprised that they have that process under good control. So they state that the gas is shelf life is 12 months, and this is something that we could confirm during that experimental trial. The thing is, I can't really give you a document for that. This is just something like, this is our internal quality standard. So if we want to buy calibration gases, we buy it from somebody who is very well suited to do that. And with the company's name is SIAT. It's an Italian company, and the gases that they have provided us, we are very happy with. The thing is, the reason why we don't provide the gas is because it's just that, like, shipping gases from here to India, for example, or let's say halfway around the world, for a company our size is just too much effort, like the bureaucracy behind it. So what we usually recommend is for the end customers to place the order with that gas bottle provider, because they have all of the instrumentation in place to ship the gases around the world.
Okay. It means that the user is purchasing calibration gases from your recommended suppliers.
This is
You will
something
take
that
the
we do, yeah.
yeah. So overall responsibility will be yours to give the precise calibration and ensure that results are valid.
Exactly.
And for
We have a list of calibration gases which suits our instrument and which is also suits the production of the calibration gas. Because sometimes when you look at an application like this, the first intention would be, it would make sense, all right, I want to quantify 4 ppb of total sulfur. So what do? I take 3 compounds and I put, let's say, 2 ppb of each into the calibration gas. This is something that is very difficult for a gas manufacturer to produce. Like producing a ppb standard is very, 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 very difficult. The good thing about our instruments is that they are linear over a vast range. So as you've seen before, we typically use calibration gases in the ppm range, because we know, and we can also demonstrate that when I, for example, calibrate methyl mercaptan at 1000 ppm, I will still get accurate results at 5 ppb. But it makes it much easier for the calibration gas manufacturer to make a 1 ppm gas than it is to make a 2 ppb gas. And also, like the accuracy and the precision of that gas will be much higher than for a very low concentration. So that's usually the way we go about getting our calibration gases.
So you mean to say the high concentration calibration gases needs to be purchased, and then your instrument will be calibrated with the dilution with the carrier gases, maybe
No,
in
you
this
don't.
case, right?
You just calibrate it on the high concentration.
High concentration.
Yeah.
And so you mean to say that you are doing single point calibration?
Yes. 2
And
points.
to
Sorry,
how
it's 2. It's a 0 point, and it's a slow point for the spun. Yeah.
Okay. So the linearity, how to ensure that the really calibration line is sanctity is maintained for the linearity?
We can send you endless amounts of measurement data proving that. This is one of the good things about these types of devices, is that they are inherently linear. It's just you can't really make them non-linear. That's the good thing about them.
Okay.
We can probably share with some of our sample data with Kaushik from Matosheet, and if you want to have a closer look into that, then he can provide these data for you.
Okay. And my last question will be this calibration gases traceability. So are they providing NIST traceable calibration gases with certificate?
Oh, that is a good question. I need to find that out. I don't know it right now. I mean, we get a certificate of analysis, but I don't know the standard behind it right now. So which laboratory standard is behind the like the certificates or the quantification of the compounds in the bottle? But this is also something that we can provide once we have researched it.
Yeah, I mean, does not mean that their way of preparing is standard. It should be traceable to the NIST. Traceability must be ensured with any standard.
I know what you mean, but I don't know if they provide it to us.
Okay. Over from me. You already said that we have.
If I may interject, Kaushik, are you still here?
Yeah, absolutely.
Could you take notes, because I don't have any thing to write here, so that we don't forget anything that came from the attendees.
Yes,
Thanks so much.
absolutely.
For any local entity, there must be some traceability. So in this case also, I believe there must be NIST traceability, but you need to check and confirm it.
Yeah, I guess so. Yeah.
Okay.
I have a question. What is the LOD for carbon monoxide?
100
na,
pp 100 ppb
100
right now.
ppb. Okay. And I have another question, like suppose if we want to measure only ammonia,
Mhm.
then do you have a solution for that? Suppose
You
if
can
we want to
maybe
measure
one more thing. So I've showed it before. You can now have all these measurement methods here. So this one is especially designed for hydrogen purity. So all of the molecules implemented here are to be compliant to this ISO standard. I can show you in principle. I don't know if you can see that now. Wait, give me a second. Like, where is it? There it is. So in principle, everything that is done in this method is editable. So for example, if you want to have a method which only includes ammonia, you can have that. It's not an issue. Just delete everything else and then the instrument will only measure ammonia. You can also add different compounds if there's something of interest due to a special production process or an impurity that you know might be in your gas. You can also integrate it into the method. Usually this takes a little bit of know-how, which correlates with the ionization method. So if something like that happens, usually we work together on issues like that. So if you need a new compound or if you need a new method, you can contact Matrix Industries and then they will get into contact with us so that we can provide you with the measurement method that you need for a certain application.
Okay, got it.
How many? I am adding one more questions coming to my mind. How many, units are in India? Have you sold any unit in India? And next question will be how much service engineers or expert you have in India?
I think I can give that question over to Kaushik, if that's all right.
Yeah. Yeah. So we have 3 analyzers running in India as of now. One CombiSense analyzer at IOCL and 2 8sense analyzers. One is with FEV. The second one is soon to be installed at Bosch. So these are the analyzers. We have a team of 3 engineers, service engineers, trained on these instruments. We receive regular training also from online from V&F. So if there is any updates, any changes, anything of the sort, they give us online training. We also provide online support. So we can provide the support from our team also online. So from our colleagues at V&F, even they can give it. So,
Is it possible to visit your customer site?
Pramodji, I believe your IC engine is being tested on the test bed at FEV, where FEV is using our 8sense analyzer. So I'm sure you have more than enough right to ask them to come and see the analyzer.
And at IOCL location, which location you have given your unit?
R&D Faridabad.
Faridabad, okay. Not at Baroda.
No.
Okay.
I have a last question.
Please.
Which technique you are using for CO measurement?
CO is infrared.
Okay, so you are like you told now ki you are buying analyzer from separate vendor.
Exactly. Yeah.
So which vendor can we know?
It's Siemens.
Siemens. Okay. Okay. Thank you.
We can go a little bit longer if there are any further questions. Otherwise, I don't know. I'd like to thank everybody for attending. It was really pleasant to have so many people listening today. Are there any further pressing questions? Otherwise, we can always stay in contact, or you stay in contact with Matrix Industries and Kaushik Shah. And if anything else comes up, we're gonna keep in touch and try to answer everything that you want to know.
One thing, can we define any particular parameter, the upper range? Suppose if I want to fix, okay, some like oxygen in the hydrogen. So if I want to fix the upper range, and if it goes beyond that, then it will give me some kind of alarm and some kind of blinking over there, so that it can give me the.
This happens automatically in the detection system. So if you
It is there, okay. But we can define the limits as per our requirement or not?
You can also do that, but there is like a hard limit, which is when our detection system goes into overload. This is when the instrument will give you errors and warnings, so that there is too much signal on a certain compound. And there is another way to give you like a warning level that you define yourself. But this pretty much is always in connection with the fully automated solution, because this is then checked, like these manual levels are checked with a piece of software then.
Okay.
Also, as you told, this formaldehyde, formic acid, and ammonia, you make a single point calibration. So already is permissible limit is 0.2. So at which level you make this calibration for formaldehyde, formic acid, and ammonia?
At 1 ppm typically.
1 ppm. But it's means already his limit is 0.2. Then it's valid to calibrate with 1 ppm.
Yeah, I can show you the data. That's not an issue.
Okay, so means with 1 ppm you can also give the result with less than 0.2 like that.
Yeah, exactly.
Even this, okay. And what is the LOD, means limit of detection for these three components, formaldehyde, formic acid, ammonia?
Wait, let me have a look. On ammonia, on this device that's standing behind me, I have a 2.3 ppb detection level. For formic acid, I have 1.2 ppb. And the last one, let me just check. Formaldehyde is 2.8 ppb.
8 ppb, huh? All these?
2.8 on formaldehyde.
2.8. Okay, means 2.3, 1.2, and 2.8.
Yeah, exactly.
Okay. Okay.
Okay, Kaushik, do you have any final words?
No, any questions from the participants? I hope everything has been covered. In any case, my contact details I have put up also on the chat box. So you can take a look at that, and please feel free to let us know if you have any questions. In the days to come, we will prepare a final version of the recorded session, and we will be forwarding the same to you via Google Drive link, so that you can also go through it at in a second time or whatever, to cover all the subject matter. We know that we've covered a lot of ground, so everyone may be also thinking about certain points, and it may come up later on. So please feel free at any point in time to contact us, and we'll be happy to help.
Yeah, Kaushik.
Yeah. Yeah,
thank you,
from our side in Austria as well. Very big
Thanks
thank
for
you
arranging this
everybody for investing their time and joining the webinar. I hope it was interesting, and I wish you all a good rest of the day.